Penguin Random House Audio presents Supermassive, Black Holes at the Beginning and End of the Universe by James Trefil and Shobita Satyapal. Read for you by Fred Sanders. Prologue. Out of the cradle, onto dry land, here it is, standing, atoms with consciousness, matter with curiosity. Stands at the sea, wonders at wondering, I, a universe of atoms, an atom in the universe. Richard Feynman, What Do You Care What Other People Think? Further Adventures of a Curious Character. It's 7 a.m., and I'm driving down a mountain in a large four-wheel drive vehicle. Barely awake, exhausted, I notice that my fingers have turned blue. I have never driven a truck before, and now I am hurtling down one of the steepest and toughest roads in the world. I feel the brakes overheating, the truck skidding, and I watch the sunrise, wondering if I'm about to drive off the edge. I shouldn't be driving this truck, descending from an altitude of 13,796 feet, 4,205 meters, at the summit of Mauna Kea, the second highest peak on Earth, and by some measures the highest, where I have spent the night observing the night sky. The black sand beaches merge into the deep blue sea below. I look to the right and see that my backpack has fallen off the passenger seat. Inside is my computer, which holds the data we obtained from last night's observing run. There is a little secret of the universe hidden inside that backpack. My fear and sense of a separate self dissolve into the sky above as I reflect on the data on my computer, a gift from a few photons that traveled 47 million light-years to the infrared detector attached to the end of the NASA Infrared Space Telescope, IRTF, where I had been granted 4 nights of observing with an infrared spectrometer. Mauna Kea is an inactive volcano on the island of Hawaii that is home to several large observatories. According to Hawaiian tradition, it is a deeply sacred and revered mountain. As I drive down the winding road from the valley below to the summit above, I honor its ancient history and feel gratitude for all that has been enabled by Mauna Kea in my lifetime. Founded in the late 1950s, the observatories at its top have allowed humanity to peer into the universe at wavelengths that were unobservable through most of human history. At sea level, there are almost 5.5 quadrillion tons of atmosphere above us, providing the air we breathe, protecting us from harmful radiation from space, creating the pressure we need for the liquid water that flows on the surface below. This indispensable blanket that protects our planet makes infrared astronomy hard, very hard. It's why I'm on this mountain, barely awake and freezing, gripping the steering wheel. In fact, the science that I want to do is impossible to carry out from the ground at lower altitude. This is because the infrared photons that we have collected, now stored on my computer, cannot make it through the atmosphere. They are absorbed by the precious water molecules found in Earth's atmosphere. For that reason, we have to build observatories at high altitudes or launch them into space in order to be able to do infrared astronomy. Last night, we peered into the heart of the galaxy NGC IO68 to study its central black hole. NGC IO68, or Messier 77, is a spiral galaxy almost 47 million light-years away in the constellation Cetus. It was discovered by the French astronomer Pierre Messon in 1780, before we even knew that galaxies outside our own existed. There, obscured by clouds of gas and dust, invisible at optical wavelengths, lies a feeding black hole. It's not just an ordinary black hole that forms from the death of a massive ordinary star, but a supermassive black hole with an estimated mass of over 100 million times the mass of the Sun. How did it form? How does it grow? What does it do to the galaxy that surrounds it, and what will be its ultimate fate? We don't know the answers to these questions, at least not yet. In the past 4 nights of observing on this revered mountain, we were fortunate to see several galaxies in which we think supermassive black holes reside. The data recorded the light emitted by matter orbiting close to the black hole, swirling around the center at speeds of several hundred kilometers per second. By measuring the speed of gas, we can measure the mass of the central supermassive black hole. We can also study the properties of stars around the black hole. How many are there? How old are they? How are they influenced by the black hole? It turns out that matter isn't just sucked into black holes, it is also often being expelled from the central supermassive black hole at tremendous velocities, sometimes approaching the speed of light. In fact, black holes can fling out the mass equivalent of an entire galaxy deep into the void of intergalactic space. All of this information about the stars, gas, and the supermassive black holes is encoded in the spectra stored in my laptop in my backpack. I sit, sleep-deprived, in a hard plastic seat in the airport, waiting to board a 14-hour flight back home. It will take months for us to fully reduce this data, but I'm going to get started on the plane. Join us as we take you through a journey from the early history of black holes, of how they arose as mathematical predictions of Einstein's theory of general relativity, to how they became real astrophysical objects that can be almost 100 million times the mass of the Sun. We will bring you up to speed on the latest research on these invisible beasts, now found to be lurking in the hearts of galaxies only a few 100 million years after the Big Bang. My airplane ride will last a bit more than half a day. Getting to this point has required thousands of years of scientific discovery. More recently, it has turned on the critically important discovery that black holes exist in the first place, and that some are more massive than others. This scientific journey takes us to the desk of the brilliant scientist Albert Einstein, whose general theory of relativity helped us predict black holes before we even saw them. Our whirlwind tour of the universe begins just a few 100 million years after the Big Bang, 13 or so billion years ago. Chapter 1. From Newton to Einstein. The Khazars believe that, deep in the inky blackness of the Caspian Sea, there is an eyeless fish that marks the only correct time in the universe. Milorad Pavic, Dictionary of the Khazars. The universe used to be such a simple place. Events ticked along like the hands of a clock, driven by simple laws that were not only knowable but known. Behind the surface complexity of the world, there lurked an amazing simplicity. Perhaps nothing better exemplifies this way of looking at the universe than the work of the English scientist Isaac Newton, 1642 to 1727. In a period that will be familiar to modern listeners, the appearance of the Black Plague in England led to what we would call today a lockdown, and Newton was forced to spend 18 months in isolation on his family farm. During those 18 months, he developed differential calculus, integral calculus, the law of universal gravitation, the theory of color, the laws of motion, and a few miscellaneous mathematical theorems. All we can say is that if listening to that list makes you wonder what you've accomplished in the last few years, you aren't alone. For our journey into the heart of black holes, the most important item on Newton's list is the law of universal gravitation. As Newton stated it, this law says that there is an attractive gravitational force between any two objects in the universe. The size of the force depends on the mass of the two objects and the distance between them. Double the mass of one of them, and the gravitational force doubles. Double the mass of both of them, and the force will be 4 times as strong. The gravitational force gets weaker the farther apart the two objects are. Double the distance, and the force will be 4 times smaller. Triple the distance, and it will be 9 times smaller, and so on. The equation that describes the gravitational force between bodies of mass, small m and large m, separated by distance, d, is F equals g small m large m over d squared, where g is a number known as the gravitational constant. The Newtonian universe. According to Newton, who described the event later in life, his discovery of universal gravitation was triggered by seeing an apple fall from a tree at the same time he saw the moon in the sky. He realized that there had to be a force acting on the moon, otherwise it would fly into space instead of staying in orbit. He also realized that there had to be a force acting on the apple to make it fall. In one of those insights that seem so obvious in retrospect, but that takes a genius to see for the first time, he asked whether those two forces, one operating on Earth, the other in...
Sample complete. Ready to continue?